Hello everyone, my name is KIM Iqbal. I'm a graduate student of Civil Engineering Department at Drexel University. So I'm doing my PhD in structural engineering. My research is mostly on structural health monitoring using non-destructive evaluation. So one of the major tools that requires in non-destructive testing is to understand how the different kinds of waves travels in materials. So to understand that, sometimes we need to model in some finite element tools to see how these things actually travels in the in a different kind of materials. Okay, so I'm going to prepare some tutorials on how to actually model the wave propagation in different kind of materials, also different types of waves like the longitudinal waves, the flexural or the shear wave, and the torsional wave. Okay, so here is actually part of my, I already created some of this. I'm just going to show you some results and then I'll move to start it from the beginning. So if I go to these results and if I see the time history, so you see it's difficult to see the wave is traveling, but it's difficult to see how they looks like. So to see it more clearly, I'm going to increase my scale factor. Okay, let's make it okay. Only this time, yeah. Okay, so let's start it from the beginning. So you see both the longitudinal, you see the longitudinal one is traveling more faster, and the speed of torsional and the flexural mode for a particular frequency in steel is almost close enough. That's why they are moving actually together. You can see both the flexural and the torsional mode. They are actually moving together. On the other hand, this is the longitudinal mode. So all of them are together. But I'm going to show you how you can generate the longitudinal mode, the shear mode, and the torsional mode separately. Okay. Okay, so let's start. What we are going to do with we are going to start with this ABAQUS standard explicit as an initial part steps. Okay, let me save this model because last time I can recall I prepared this, but I didn't save the model. So let's okay, let's make it. Okay, so first you need to create a part. These times we are going to choose the 3D, and also the base feature should be solid and extrusion. Just since I am showing you how you can do it, right now we are focusing on these things. I'm not going to describe how these things actually interpreted. I mean, if you take finite element analysis courses, you will definitely know these things actually. Okay, so this is my grid view. Okay, before starting, I'm going to create. Okay, let me give me some. So before telling before starting, let me show you something actually what I'm trying to do. So this is a published articles that has been published by the researcher of this group, and in 2019. So I'm trying to actually show you kind of a replicate of what they are doing, but not almost same. So this is actually the steel wire. Okay, and I am going to use this tone burst, and for the properties of the steel wire, its dia is 7 millimeter, its length is 500 millimeter, but I am going to use 1 meter. Okay, and they are going to use density 7. They use 7,800 kg per meter cube, but I am going to use 7,850. And Young modulus is 209. I am going to use 200 gigapascal. Poisson ratio is same. Okay, and I will discuss these slides or this page later. Let's begin first. Okay. So since I have to define my cross section first, what I do, I define through the coordinate system. You can see here I put 0, 0, enter. And now I'm going to put my diameter 0.0035, sorry, radius. Okay, and it's very tiny, right? But if I click done, so the first thing first, in ABAQUS, when you are generating a part, defining properties or creating something, you need to be consistent with the units. Okay, because ABAQUS doesn't know it doesn't have any default units, so you have to be consistent with the units, the things you're using with the same consistent units. So it's you are the guy who need to be careful. So as I mentioned, my length or the depth of the pipe will be 1 meter. So that's why I'm using 1. Click OK. You see my pipe is already generated. Okay. And for now, okay, let me create some datum points at the middle, because I'd like to see when I apply some tone burst on this side, I want to see how the time history of a particular point looks like. Okay, so for not only on this point, I want to see on the middle, and I also want to see at the end. So let me create a datum point and set XY plane and make it 0.5. Okay, you see a datum point is created, and let me partition this guy. Okay, so this is the datum plane I'm looking for. So my pipe is actually divided into 2 segments. They are still connected, just 2 portions, you can say. Okay, so there is nothing I have to do here right now. Super academical. Okay, now let's go to the property module. Okay, so my property is steel, and the density of steel, as I mentioned, I will use 7850 kg per meter cube. And the modulus of elasticity, Young modulus, I am going to use 200 E9. Okay, and the Poisson ratio as 0.3. Okay, okay, and then I have to create a sections. I'm creating sections solid homogeneous, and the material I'm using is steel. Okay, and then I have to assign these sections to this guy. So I'm selecting both. Okay, click done. Click OK. Okay, so I am done with this part also. Now let's go to the assembly. Since I have only one part, I don't have to worry about others. I just leave as it is, click OK. And then the step modules. Okay. So in the step modules, since wave propagation modeling, it's a dynamic problem, because you want to see how your wave is traveling with respect to time, how the deformation is occurring in different times. So it's a dynamic problem, and that's why I am going to choose the dynamic explicit now. There is 2 things. One, you need to define your time period, and also you need to define your step time here. So the thing is that the time period you can calculate by this way. Let's say the longitudinal mode, it starts from this point, then it goes back to this point, then it will return, and it will come back again at this point. Okay, so if you want to see only like one cycle, go this point and this return this point, you want to see only one cycle, then you are traveling twice the distance of this pipe. So you can calculate your time period by 2 time distance divided by the speed of the wave in steel. So there are a lot of equations available to calculate the speed of the wave in steel, or we generally know it's almost close to the 5,000 meter per second, right? So you can, by this way you can get. So what I am going to do, instead of using I want to see another cycle. So instead of using 2D, I will use 4D. I mean, the D is the length or the depth of the pipe or the steel wire. So by this way, if I calculate, that will be 0.00. You can calculate it by your hand. That's what I can say. The second thing is that the incrementation, it's the step time. So if you choose automatic, ABAQUS does it for you, so you don't have to worry about it. But I prepared to use my own, and maybe I will prepare another video how you can actually choose your step time, how it depends on your wave looks like. I mean, a lot of things actually depends on this guy. So right now I am using my step time as 1e minus 8. Okay, and this is something actually need at discussion, but let's say for now let's skip that discussion. Okay, and the second thing is that we need to define the field output. There is already one field output there, so we need to choose what we are looking for. No, I don't want to see the stress, strains, no force, no contact, no volume. I only want to see the translations and rotations and the accelerations, I mean translation and rotation accelerations. These things I want to see. I want to see for the whole model, but not for 20 intervals. I want to see for the 1000 intervals. Okay. And click OK. Done. So the next thing is that the history output. So field output prepare the analysis for the whole model, but if you want to see how the wave is traveling on a particular point, especially, then you need to go to the history output, and that will prepare for you more details graphs or the more detailed explanations or outcomes actually. So for this reason, as I mentioned, I want to see for a point here, I want to see how the wave is traveling on this point. I want to see how the wave is traveling on this point and also on this point. These 3 points, I want to see more details. Okay, that's why you need to create a history output. So before creating history output, I need to create some sort of sets. So how can I do that? If I go to the assembly module, see here is the sets. If you click one, let's choose set as front. Click continue. So choose this one. Done. And click another one. That is it. Continue. Done. Let's get another one. Sorry. Okay. Done. And another thing, let me create a surface also, because I would like to apply my longitudinal tone burst on a surface, not on a point. Okay. So let's do this surface. Done. Yeah. Okay. So now if I go to the history output, let's say click edit. No, I don't want to see the history of the whole model. Then it will be huge for the ABAQUS to handle. I mean, you'll need a lot of computational time. Also, you need a lot of space. So I don't want that. I want only some specific sets or some specific points. So let's say it as int, okay? And I want to see every n time increment. So that is something actually will define how many numbers of data you are looking for a particular signal. Okay, let's say the sampling rate we can say. So right now, if I put n equals to 1, I am actually storing almost close to the 1 megahertz, 1 million data per second. So how do I know this? Actually, I already defined my step time as 1 e minus 8. Okay, so yeah, that's why I need to actually create another video on describing that parts. So let's put like this way for now. Okay, so oh no, let's uncheck it. Yeah, I want only these three guys, and here I only want to see the accelerations, not the rotational accelerations. Okay. Okay. Let's rename it. It's this is for the end. Okay. Now similarly, I want to see for the middle guy. Continue. Set. Here. No. Yeah. This is one. I want to say all of these three guys. Okay. Okay, let's create another set. That is for the not, which is actually not needed, but let's do it. Okay. Okay, so all of the things have been done here. The next step is to interaction, but I don't have any interactions. I am creating only one part, so I don't have to define interaction right now. And I'm not going to assign any boundary condition also, because ABAQUS in dynamics, ABAQUS can analyze even if you do not apply, define any boundary conditions. Okay, now let's go to the load module. So I would like to apply as a pressure. Okay, and click continue. Also, I already have a defined surface, and this is my surface. You can see this is my surface. Okay, okay. Here is the thing. Since I am going to use the tone burst, let me show you one of the tone bursts. Okay, now is the time to discuss about this bigger section. So if I am going to apply, let's say when you hit a metal or something with the impact hammer, you're actually, the time history looks like something like this. It's not a triangular, it's kind of parabolic shape. Okay, but what happens is that it comprises a lot of frequency, and you can actually, from the amplitude versus time graph or the time history graph, you will not be able to see how many frequencies are there. But if you do the 2D FFT, then you will be able to see the number of frequencies there. Okay, so you see, even this is looks like a very simple graph, but it comprises a lot of frequency. So if I am looking for to generate some specific frequency, to apply some specific frequency, on my steel pipe or steel wire to generate the longitudinal or the shear or the torsional, then you need to actually use something called tone burst. So a tone burst is something looks like this. So you can actually generate this tone burst by using actually the Henning window. Okay. Okay. So there is no Henning window right now, but anyway, you can create using the Henning window. But let's. So I mean, you can create the tone burst by you can generate a sinusoidal wave. Okay, and that sinusoidal wave you can actually as you can actually create the frequency you can looking for, and using the Henning window you can get this tone burst. Okay, and I'm not going to actually show that part. That is another discussions. But if you do the FFT of this tone burst, you see the maximum energy is stored here or up to this frequency. So it's a kind of a single frequency thing. Okay, so this tone burst is for 60 kilohertz, but I am going to use in my analysis for the 100 kilohertz tone burst. Okay, so you see this is my tone burst and these are my data. So I'm copying it and I'm going to, so here I need to define my amplitude. Okay, if I click create amplitude, if I go to continue, you see, so here you can input your time versus amplitude data. Okay, and yeah, click. Okay, now choose here the amplitude one. And regarding the magnitude, so right now I am going to use only one, but in some cases, let's say you want to see your actual behavior or when you are hitting through the a real or tone burst by your let's say you are applying some force, you know how the maximum amplitude is, so you can actually incorporate that magnitude value over here. You can adjust it. So right now I'm skipping that part too because I'm just showing you how you can generate the longitudinal model. Okay, I mean, even though you change the magnitude, it doesn't matter. The speed will remain same, but there are some other properties that needs to be actually, that will be different if you use higher order magnitude. Okay, so you see my loads are applied here. Okay, it's showing 3 points. I don't know why, but it should show a lot. But I am sure they are over there. Don't worry about it. Okay, so we are done with the load modules. Now the next step is to do the mesh modules. Okay. Okay. So let's do on the part. Let's seed the first. So I'd like to make my mesh size 10 millimeter. Okay, 0.01. It's 10 millimeter. Click apply. Okay. Now mesh it. Yes. Yeah. You see my mesh is generated, but I'd like to make a more refined mesh. Okay, so this is good and this looks okay, but I'd like to make more refined mesh. So instead of using 0.01, let's use 0.005. I'm actually, that was 10 millimeter. Right now I'm making mesh size smaller, so it's 5 millimeter. Click apply. Yes. Okay. Yes. Okay. Oh, it's still the same. Okay, let's do it again. Let's make it 1 millimeter size. Click apply. Yes. Okay. Okay, so I made my mesh size more smaller. Okay, and it looks like now it's really good. I mean, if you make mesh size smaller, you need to give ABAQUS more time to compute your finish the simulations, and In terms of money, you need more money actually. So it's up to you. You decide what will be your mesh size look like. But one thing I'm going to tell you is that even though you make a smaller size of meshes, you see it's not symmetric. So this mesh is not symmetric. If I go on the other side, still the same, it's not symmetric. So whatever your mesh size is, you need to make sure that your mesh looks like symmetric, because actually otherwise you will have different kind of local deformations, and you will not generate the actual longitudinal mode you're looking for. So that's why let's go back to my art module. Okay. Because to make it properly mesh, I need to do something at the beginning. So what I can do, okay, 3 points, yeah, okay, so just this node, this node. So this is something I am doing to make sure my mesh looks like symmetric. Okay, you definitely find another way to do that, but I found this is the most convenient way for me. 3 points. Let's go to the mesh now. Let's make it 0.001. Okay. Okay. Now let's see this time how the mesh looks like. So you see, the mesh is symmetric. Okay. We go to the other side. Yeah. So now I have created a symmetric mesh. So that's what I was telling you guys about. So you need to be careful. You can actually change the mesh size if you want, but let's keep it as it is. So everything is done. So now let's run this analysis. Good job. Let's make it okay. Genius. It's multiple processor. It's up to you. I always use multiple processor. So before submitting the analysis, I am just let me go to the load module again. So the reason I applied my load on this surface is that we know that the longitudinal mode travels along the axis of the materials. Okay, so if you apply on these directions, it will go directly through. It will travel on these directions, so actually in the z directions, right? And what will happen in the longitudinal mode? We know that actually the load actually, the wave, sometimes it squeezes, sometimes it expands. Okay, that's the way it travels. And if we want to create the flexural mode, we have to think something different. That I'll show you in another videos, but not on this. Okay. Okay, now let's finish this. Let's submit it. Yeah. So I have submitted it. So okay, now it's submitted. So okay, so it will take some time actually. So I mean, I'm not sure. For me, it generally takes 30 minutes because I used a refined mesh. So there are a couple of ways you can reduce this analysis time. One by decreasing the step time, another one is by decreasing the time period, and another one is by increasing the mesh size. So these are the ways you can do. It's up to you. So okay, we'll start after the analysis finish. I will show you in the next how you can interpret this data, how you can extract the accelerations, time history graph, and how you can calculate the speed of the wave in this steel wire. Okay, yeah, just give me a couple of minutes so that this analysis is finished. Okay. Recording. Hello everyone. So my analysis has been finished. Before this showing you the results, I want to mention one thing. So if I go to the step, you can recall I used this time period as 0.008. So I figured it out that that was really high. So I reduced it. I just put 0.001 and I did the analysis. I didn't change anything else. So how did I get these values actually? So this is what I tried to mention you earlier. This is the length of the steel wire. It's 1 meter, and I assume the speed in this is 5,000 meters per second. So if wave starts from this point to this point and come here again, it travels twice of this distance. That's why I multiplied 2 times 1. And I want to see twice of these things happening. That's why I have to multiply 2. And this is the whole distance, and this is the speed. And then I get the second or the period I needed. So I just increased a bit. I used 0.001. Okay. And that's what I did just to show you. Okay. Again, that's what I did. So now let's go back to my analysis. So you see everything is completed. Dismiss. Let's go to the job, go to results. Okay. So before seeing the results, okay, let me choose this one. Okay. So I'd like, so I already scaled it to see more clearly. Actually, you see, you can actually increase your scale factor up to you. If you choose the auto, you will see the wave is traveling, but you will not see that much deformation. So I want to see the deformation also, and I choose the visible edges as free edges so that I can clearly see how the waves are traveling. But you can actually, it's up to you whatever you want to see. Okay. There are some other ways. Let's say if I go to the contours, I can choose the ISO surface. Let's see how it looks like. Oh, okay, then in that case, let me go back here again. Oops. No. Okay. This is something actually you can play. No, let's leave it as it is. Okay. Okay, so I want to see how the time history looks like. So instead of making it fast, I'm making it in the middle, and I want to see only once. Apply. Okay. Okay. So you see the wave started traveling, right? And you see, can sometimes it's expanding and it is squeezing. So that's the how longitudinal mode travels, right? And over the time, it's traveling. Let me increase the speed a bit since it is slow. Okay, so you see, and then it's reflecting, so there is a lot of deformation going on in this area. Again, it got stable, it's traveling. Okay, so this is the way you can see how your waves is traveling. Now let's see how we can actually see the time history graph. Okay, so let me create another viewport. Let me tile them. Okay, let me create 4. Okay, 3, 4, and let me tile them vertically. Okay, and I want to see the wave traveling on this guy. And what I'd like to do, I'd like to actually no, 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 no. Apply. Nothing is here. Okay. I want to see only the wave travel. That's it. So on this guy, I want to see what happened to my accelerations. I want to see only the longitudinal direction. That's I'm choosing A3. You see the longitudinal direction is the Z direction. So that's why I'm choosing A3. And I want to see first on the front. Okay. And here, I want to see what happens to the meat. And here, I want to see what happens to the end. Okay. Done. So now I can, let me rotate this guy. Okay. And now let's link these viewports. They all are linked. So now let's play the time history again now. Okay, hold on. Let me start from the beginning. Okay, you see, so this is the front, and you see that there is a wave at the front. Right now, there is no wave. Again, yeah. And when the wave reaches to the midpoint, you see the mid. I would select some nodes at the mid, and you see how it looks like. And then it goes to the end. You see how the ends looks like. So here's another thing you need to notice, both on the front and at the end, the maximum amplitude is 0.03, while at the mid, the maximum amplitude is 0.015. So the reason you can see when it's actually the wave reached at these nodes, let's look at this point now. So it's reflecting, you see. So that means two waves, they are actually submerged, superimposed. So that's why its amplitude is increased. Okay. Okay, so that's our waves generated. Now let's see if we can calculate the speed from this. Okay, let's do another thing. Let's link this viewport again. And what I would like to do, I'd like to save the video, okay? So that, let's say you want to show these things to someone else later, you can do that. So let's run the tutorial 2. Okay, let's make it much 25. Okay, click apply. So I hope the video is created. Okay, done. Now let's export the data. Okay. So what you can do, Yeah, you go to the PDXY data, click continue, and choose A3. Okay. And I want to see the HE for the middle. Click save as. Uh, let's let's save as it is. Okay. No, I don't want to support the curves. Okay. And then this is save as. No. Okay. Then this is late. So next thing we can go to the tools, Excel utilities. So we'll see these three are already here. So I'm going to move this one first. Click OK. It's converting to the data is converting to Excel files. I hope it will not take that much time. So while it's generating, let me show you something. So this is some small codes that I tried to develop. So we used the modulus as 200 E9, right? And the Poisson ratio is 0.3, the density we use 750, right? So this is the longitudinal speed as per theory, 5,856.4 meter per second. And this is the shear wave, 3,130 meter per second. That's what we are supposed to get from our the analysis. So let's see what we're getting. So I don't know why it's taking too much time. Hello everyone. So it took a lot of time to convert the data from, from the ABAQUS to the Excel, because I saved a lot of data. 10 megahertz data. So it's very huge in size. So that's why it took a lot of time. Now, if I click run, what I have to do is that this is a code that I developed to calculate the speed. Okay, so it's actually what it's doing. It's generating the plots for me right now. Yeah, so this is the plot, and what I have to do is that I have to select first couple of points, and then this is my second rep, so that I can see more clearly the first arrival. So you can see this is the first arrival, and here yeah, this is the first arrival. Okay. Let's see how is this speed calculated. Okay, so speed is 48507. 4,850.7. Let's try again. So the ideal way is to choose a lot of sets. This is only for 3 points. From you need to do it for a couple of times so that you can actually clearly distinguish between the first arrival. So this is first arrival here, and this one is the first arrival here. So yeah, so what I'm getting is speed as 5,008 meter per second. Okay, so if I go to the theoretical values, I think I showed you earlier that we use 200 E9, 3, 7850, and here it's a 5856. So there is a difference between my that speed and this speed. So that's the another discussion, but I'm not going to discuss that. But it's happens due to the dispersion of wave in materials. So that's another part of discussion. So thank you so much. In the next videos, I will prepare or show you how you can generate the flexural wave, and the following video, I will try to show you how you can generate the torsional wave, and maybe I will prepare a video on how you can actually choose your step time, period, and how it's actually related with the sampling or how many data points you're looking for. So thank you so much for watching these tutorials. Please ignore if you don't understand. I mean, excuse me if you do not understand some of my English. I'm international student, so that can cause you some difficulties. And another thing is that if you see I did describe something not correct, you can always make a comment and let me know, so that I can actually either update or I can correct myself for future. And thank you so much for watching again.